there's one very special acceleration, and that's the acceleration caused by the gravity. So the Earth actually pulls any object down towards itself at a constant acceleration. And we can actually find what that acceleration is now with the tools that we have. And I have written it down here. So it's 9.80665 meters per second squared. And it's down. Now, what does that mean? It means that any object, and you can, of course, test this on your own, near its actual Earth's surface. Now, the word near, okay, just depends, okay, you know, how far and, you know, what does that near actually mean? But anything that you kind of throw up, kind of up in the air, okay, or you let go is going to start to accelerate at this particular rate. Now, the assumption is that we do not have any resistance. Now, this is obviously false near the Earth's surface because we do have air resistance at the minimum. Now, the air itself has particles, and any object that goes through the air is going to be hitting those particles on the way down, so it's not going to accelerate exactly at this rate. But when you're in grade 11 or when you're starting your physics journey, and even if you go on into higher kind of physics, you will be using this particular rate. And it is so special that we actually do designate, instead of just calling it acceleration, okay, we give it, okay, the letter G. And this particular G is equal to 9.8, 0665 meters per second squared. And it's down. Now, when we say down, we mean towards the Earth's surface, right? So towards the center of the Earth. That's what we mean by down. So, of course, it will depend on how you are abbreviating kind of your actual, the reference points, okay? You know, up is up positive or is down positive. So we're going to have to be careful there. Okay, and you know, so that is something that I'll actually discuss in just a moment. Now, we don't really want to be writing out the full acceleration, so we typically approximate it, and what we do is, you know, we basically will approximate, and you'll see this in numerous textbooks, that they'll just simply use 9.8 meters per second squared instead of the long kind of, you know, it has 5 decimal places as your acceleration. So this particular acceleration, as I say, it means down. So wherever you are, so if, you know, if this is the Earth's surface, okay, as you're going along, so any object, okay, that you have in here, so this is going to get pulled down. So notice it's a vector, and it's going to be down at 9.8 meters per second squared. So that's what we mean. Now, if for whatever reason, and this is what you have to be careful, if you have your reference and you say that up is positive, right? So if you say that up is the positive reference point, then, you know, all of a sudden, okay, this becomes negative 9.8 because obviously it's in the opposite direction of up. So just be mindful of this, okay, with the actual gravity. It shouldn't cause you any kind of harm which way you define, you know, is up positive or is down positive. Just be consistent. So whatever you choose as your reference point, you know, stick to that particular reference point throughout. Now, if you're doing problems with this, it's not any different from, you know, any equation that you have used for kinematics in one dimension, and you have, you know, have gone through 5, 6, you know, or more equations, and maybe I'll put up a link up above there to all the different equations. And wherever you would see acceleration, you know, you simply would use that acceleration. And because this is so special, it's caused by the pull of the Earth's gravity, you know, we designate it with G. So instead of writing A for acceleration, you can be very specific, okay, and you can say G. Now, as you go on, you know, as you finish kinematics, you know, and you continue on, and then maybe you'll get into dynamics where you study forces, this gravity will be kind of important, right? So it's going to relate it back to weight, okay? There's going to have all kinds of different relationships that you will have for forces, okay? Which are just basically pushes and pulls, okay, in various directions. So how would you run into this acceleration due to gravity, and where would you use it? So here I want to just give you an example, and I think through an example, hopefully you're going to understand, okay, what we're referring to. So let's imagine, let's say we have some kind of a ledge right here, and someone is standing up on the ledge, okay, so right there, and this particular person maybe is holding an object, right? So this particular object gets tossed up in the air, and I'm going to just, for the sake of simplicity, let's say that this is tossed up at maybe, 10 meters per second, okay, and it is up. And I'm going to make up positive, all right? Now, if I make up positive, so I have to make and create now a reference. So where does 0 start? And I guess 0 is going to start from, right from the point, okay, where it is tossed up. So let's make this reference in this case. So this would have been 0, okay, in terms of your reference for position, right? So it's being tossed. Okay, so this is 0 meters right there that you would have. Now, once you choose up to be positive, and this is your reference point right there, then your gravity, which is going to start acting on this, you know this, it doesn't matter how hard you throw something up in the air, it's coming down, okay, because what's going to happen, okay, to this particular object as you're kind of moving along, so this particular object is going to try, okay, and it's going to go, up all the way, and let's assume, I mean, it's going to would be difficult to do, but let's assume that it's just vertical because we're talking about one dimension. So it's just kind of, all the way up, and, maybe let's kind of shift this, okay, over just to provide some kind of context. So let's say, it's thrown around that ledge, okay, and you're standing right here, and then it goes up. Now, it's going to have the fastest speed in the beginning, right? So this would have been like your V initial, okay, so it's at 10 meters per second upwards, and then it's going to keep traveling, but, okay, what happens here is that you do have your acceleration due to gravity, so your G right here is pointing down, so this would have been minus 9.8 meters per second squared, and with respect to the reference of up, okay, so that's what it would have been. Now, if you put 9.8 meters per second squared down, then it won't be negative because, you're putting it down, so that means the inverse, okay, would have been the negative. But if I've chosen up, okay, as my positive, then I'll just stick to the up directions just so that I'm consistent all the way throughout. So that acceleration really is that deceleration of this object, and it would just continue upwards until eventually, as it would carry on its own. So this thing would just simply eventually just kind of stop, right? So it would have, let's say if this was your V final right there, okay, well, that particular object eventually is going to stop moving right there because gravity is trying to pull it down. And now when it stops, obviously it's going to start to come right back down, and as it comes down, it's going to continue. I mean, unless you catch it, it's going to continue straight downwards, okay, as you're continuing down there. Now, this particular cliff, let's say, maybe there's some kind of a distance right there that it would have, and we don't necessarily know what that distance is unless, it is given to us. But for the moment, how would we be calculating and doing calculations here, and what could we possibly be interested in? Well, one of the things that you can be asked about is, how long will it take for that object or that ball to actually stop, right? So as you throw it up, it doesn't matter how hard you throw it up, okay? Eventually it will stop, so how long, how much time would elapse there? So that's actually not a very hard problem for us, because what we know is from the viewpoint of our acceleration equation, so we know that the average acceleration, okay, that we have, now in our case it's just g, okay, in here, it is equal to the change, okay, of velocity with respect to the change in time. So if you know that you are dealing with gravity, okay, pulling it down, so it's going to be negative 9.8, and your change in velocity is v final, which is 0, right, minus your v initial, which in this case was 10, Notice the units are all aligning, so just make sure that's consistent. And then, this would have been divided by the amount of time, okay, that this would take. And we are assuming, again, there's no resistance, right? And this is what you typically do in introductory physics courses, so you can certainly make that assumption. So what would this be? Well, this would have given us, so delta t, if I bring this, okay, over to this side, and then I bring this and I divide both of these by 9.8, so this would have been negative 10, right? And then divided by, and this is negative 9.8 right there, and then you can find out the two negatives will cancel. Now, technically, you do have two vectors, right? So this is really a vector, and so is this. These two are vectors, and you can't really divide the two vectors. However, we are kind of interested in the magnitudes, okay, on their own, and then the directions, are taken care of, okay, with respect to how we set up the problem. So, you can't really divide vectors, but if you substitute this in, on the assumption that they're in one dimension, right, and they're in the same dimension, okay, this will work, right? But do keep your signs in there so that you know what's happening. So now, negative 10 divided by 9.8 is actually going to be, so this is 10 divided by 9.8, which is 1.02, etc. Okay, so this is 1.02 seconds. Now, if I want to be kind of consistent, okay, so throughout, let's assume that we want this to be to 3 significant figures, okay, in terms of rounding. If it's only to 2 significant figures, then my answer is just 1.0. And that is just about a second that it would take. So if you toss this up at 10 meters per second, it's only going to take about a second for gravity to really slow this down, right? And then it's going to start coming back, okay, as you're going through. So that's one of the things that you will run into. And in all the questions, acceleration due to gravity is just the 9.8, right? So sometimes, you'll round it to 9.81. Rarely will anyone actually use the entire, okay, all 5 decimal places. In fact, I don't typically remember them. I just did it for this video. But I do use 9.8 or 9.81 in terms of rounded, and it is always kind of down, all right? So that's one question that could be asked. What else can be asked here? Well, another question that could possibly be asked is, after a certain amount of time, what is maybe the speed as this thing is falling down, right? So now, that's the actual green. So maybe, let's say that this cliff is very long, right, as it continues on downwards. And you might be asked a question, something like this. You might say, okay, so let's say after, in particular, okay, let's say 5 seconds. If you assumed, okay, that gravity, okay, g was 9.8, meters per second squared down, if you make that assumption, how quickly would something be moving after 5 seconds, right? And you can now start, okay, so within here, we'll try 2 things. A, what we're going to try is we're going to be trying, okay, this out. So what is it if my initial velocity is actually 0? So we're at the peak there, right there, okay? So we're all the way at the top. And now if you wanted to find out what your V final is, so here we would need the actual equation for V final, and this will depend on what information we have. So my V final was V initial, so this is one of the equations, plus, acceleration, okay, or the average acceleration times the change in time. So here we actually are given all of this, okay, so this is actually 0, so we're starting from 0 right here. Notice that our acceleration, okay, so again, this will depend on how you are defining it, okay, so if you want it with respect to up, right, so an up is positive, then you would substitute this in as negative 9.8, and this would have been for 5 seconds, and this would have been with respect to the up, right, direction. So here, if you would multiply this through, so it would have been 9.8 multiplied by 5, which is about 49 meters per second. Now it would be negative, okay? But this is with respect to up as being the reference point. So the negative just simply means that it's in the opposite direction, which is down. If you had it and you've defined it as down positive, you can remove the negative and you'll get 49 meters per second down, which is exactly the same thing, right? So if you write it like this, okay, or if you write it like this, both are identical. Just choose your reference wisely, all right? Or whatever your teacher asks you to do. So that's with respect to the actual velocities. Now you could start, so notice that within here, what if we started and it was 5 seconds, right? But our initial was actually the toss-up. So this was at 10 meters per second. Notice this was up in this direction. And we wanted to find out what the final actual velocity would be. This doesn't change anything for us. Now, just please make sure that you do have, or consistently, so if you do have up, okay, then now make sure that you are using the correct acceleration, okay, as you're substituting it into the equation. So this would have been, plus the negative. So it's going to be minus 9.8 because it's acting downwards, and after 5 seconds. Now, we already know that about after 1 second, so it will go, and it will stop, and then it's going to start coming down, right? So if you would do this, now this is going to tell us what that particular speed would be, or velocity. So minus, and so within here we know that that's 49 there, so I'll just do that. And this would have given us negative 39 meters per second, and of course this is with the reference up. So I'll put that so that it doesn't throw you off in terms of having that negative, which just simply means 39 meters per second down. And that's something else that you can do. And obviously this is not going as fast as it was going here after 5 seconds. Well, that's because, initially we threw this up and then it goes this way and then it starts coming down, right? So first it has to stop and then it starts to come down. So those are other questions that you might be asked. And lastly, another question that you might run into is the actual distance, right, that is covered. And this is, of course, with respect to the displacement. So be careful here, because if you want to know what the distance covered by the ball is, the distance will be, you are going to move a certain amount up, right? And then you're going to be moving a certain amount down. So now be careful. Are you interested in the distance, which would be, this path that you take and then all the way down, which obviously is longer? Or are you just interested in the displacement? And then the displacement really would be just from here to here. That's how much it got displaced, right? In terms of the actual throwing up of the ball. So be careful what they're asking you. Are they asking you for the total distance traveled by the ball? Then that way you would have to calculate two things. This would have been piece 1 and this would have been piece number 2. And you can then add them together, where piece number 1, so the distance that was covered, okay, on the first path that you had, so that would have been the displacement going up, and you started at 10 meters per second, okay, this was going upwards, and this would have been, in terms of your equation, so this is your delta D, okay, which is equal to, and now, you can do one of several things, okay? So within here, we already know how long it has taken to go all the way up. So this was the 1 second over here. So I know that it takes 1.02 seconds, okay, to go all the way up there. So I can technically, use different equations for this. So I can use the equation where I have my V initial plus V final divided by 2 times delta t. So I can use that because I know delta t, that that it goes in and it takes about 1 second to go from here to here. I do know my initial, I do know my final. Well, my final was actually 0. So I know that and how far it has traveled, okay? So that's not a big deal. I can also use another equation because I also know the gravity itself, right? So as it goes through in there. So I can just simply say 10, and this would have been the equation that you would have, which is your V initial times your change in time plus the 1/2 acceleration, right? So the average acceleration times the delta t squared. This is the longer equation that you can use right here to be able to find. Now, clearly, this one is a little bit easier to be able to plug it all in. So for instance, if I wanted to do that, okay, and I'm going to use that equation, this one. So I'm going to say that 10 plus 0, that's my final, divided by 2. So obviously it's going to be 5. And then times, 1.02, and this was rounded, okay, within here. So if I do this, well, it's going to be, so how far did it actually go up there? So this is going to be, 10 divided by 2, so that's your 5, and multiplied by approximately 1 second, okay, which is approximately 5.1 meters up that it has gone. So that's the distance that it has covered. Now, you would have received exactly the same thing if you substituted it into this equation right there as you're going through. But it would have been a little bit more annoying to be able to substitute VI, delta t, and then your acceleration, which your acceleration is negative 9.8, right, meters per second squared as you're going through. Now, on your other path, okay, so path number 2, okay, so this is for your second path. So if this was your one distance going up and now your second distance coming down, well, now you have to go from here to here. So now you have a different initial, all right? So your initial here is 0. And then all the way down, we certainly could use, okay, what that particular distance was. Now, we do have to know, how long, right, we have been traveling for. So if it does actually say for the entire duration of 5 seconds, well, then if this was for 1 second approximately, then number 2, so this delta t, okay, would have been equal to 5 seconds, minus the 1.02, which is going to be approximately 4 seconds, right? So here is what we would have. So that's my delta t for this trip from here to here, right? And you can find out what that is. Now, I don't necessarily want to be able to use V final in here, so this time around, I will use this equation right here. Okay, so if I use that equation as I'm going through here, let me duplicate it, bring it back down. So now what do I substitute? Well, I am at the top, so my initial velocity there is 0, stop there. How long am I going to be going for? This doesn't really matter, although I guess it's 3.98. Now, this we have to be careful. So this is 1/2. Notice the gravity itself, okay? So as you're going through, this is with respect to the reference, right? So if it's up, you can still put negative 9.8, okay? But this is with respect to going upwards. And then finally, we're going to get 3.98 squared over here. So what will this give me? Well, 1/2 is 0.5. This term is gone because it's 0. Multiplied by, so this is going to be 9.8, but it's negative. And then times 3.98, and it is squared. So this would have been negative 77, 0.61, etc. Didn't tell us what to round to, so we can keep it to, let's say, 2 significant figures or something, which is approximately 78, so negative 78 meters. But this was with respect to up, right? Because that's what I took as the reference. So if you wanted to know what the total distance was, well, so this was 5.1 meters as it went up, so that's 5.1, and then it came down 78 meters, so my total would have been 5.1, plus the 78 meters that you have in there. That's the total distance covered. If you wanted to know what your displacement was overall, then you are only looking, okay, if it went up 5.1 and went down 78, then you would have been subtracting those two. So those displacements would have been 51, and you would actually use the correct values in there. and this would have given you the displacement. Notice the displacement would have been this particular piece. Now, obviously, this piece is much longer there, but that's your displacement that you're looking for. All right. So did you have to break it down into two pieces if you wanted the displacement? No. So if you wanted displacement, you could have just used this entire equation right here, right, to find out what that displacement was. You could have substituted your VI, which was 10 positive. You would have plugged in the actual 5 seconds that it has traveled. You would have plugged in your gravity, which is negative 9.8, and you would have plugged in here, 5 seconds for the total, up and down. And it would have given you exactly the same thing. So this is what we would do. We would say 5.1, minus the 78, which is approximately negative 72.9. So this is from the reference, it went down that much. So we could have done it like this, or as I mentioned, let's just complete this. This would have been delta D is equal to, so 10 multiplied by 5 seconds plus the 1/2, the gravity, which is 9.8 down, and then your 5 seconds squared. And notice, if you substitute all of this in here, so 10 times 5 is actually 50. The negative will come out, so it's going to be negative. And it's going to be 0.5 times 9.8, I'm putting it all in brackets, and 5 squared. And now this, you can do that and notice what you get. So you'll get exactly the same thing. Now, the only difference is you might say, oh, you're a little bit off, but don't forget that we rounded. Okay, I rounded over here. So if I didn't round, we would get the same thing in here. So that would have been the actual displacement, okay, that you have. And the negative just simply means with respect to the reference going up. So that's how you work with these types of equations, and also how the gravity works in one dimension. What are all the possible things you might get asked? All right, thanks for watching. We'll see you in a future video. Bye, everybody.